The next session and our first discussion panel of the day and of the summit is titled Simulate to Decarbonize, Scaling Physics-Informed AI for Energy and Industry. To discuss this topic, we're going to welcome to the stage, and we're going to get them some seats here, Michel Hunsicker, Investment Director at EDF Pulse Ventures, Troy Harvey, CEO and founder of PassiveLogic, and Alex Donzelli, CEO and founder of Fainite. To moderate this panel, we'll invite the managing partner of Activate Capital, Anup Jacob. We're looking forward to this session. I think we've got the seats ready. Thank you very much. And let's welcome our panel to the stage when you're ready. Over to you.
Thank you. Get sorted. I think that, I think
that one wanted.
Yeah, I'll take this seat. When we were starting to talk about this panel and physics AI, one of the things I was thinking about was, what is physics AI? And, I think every conversation that we have now talks about the AI world that we're about to live in. And Jensen last year started talking about how AI is going to start moving into the physical world. And so I'm super excited to talk to our panelists today. I think we'll all learn together about this new interesting innovation that's going on. The context that I was thinking about was that every year we produce about $4 trillion worth of products. And so as those products are starting to have the influence of AI inside of them, I think that this is going to be a super interesting panel. So I thought maybe we could quickly start with introductions. And I think it'd be great to get your name, what you do, how you ended up here, and we'll start maybe down the line and work our way down.
Yeah. Thank you for the intro, Anup. I'm Alex Donzelli, the CEO and founder of Fainite AG. Early in my career, I was modeling the supersonic failure of aerospace materials in the States at Caltech. And that's how I realized, in the first place, how I encountered the challenges that we are solving at Fainite. Later on, I joined the workforce in the energy field, machine vision field, and I realized the same problems were also actively problems for engineering teams. And the problems I'm referring to is the time-consuming nature of simulations, the fact that they are computationally intensive, and normally this slows down product development of hardware products or even manufacturing of these processes. And due to these limitations, engineers have to make simplifications or assumptions on how a specific material or product would behave. And this reduces the level of accuracy that they can use in simulating these products, right? So to remove these limitations at Fainite, we are building a physics AI engine that carries the knowledge of thousands of engineers and can be used to solve complex engineering challenges or design challenges without recurring to these limitations or simplifications. So an example of this would be predicting the lifetime of turbines under changing operating conditions. It could be doing generative design of solar panels for satellites applications, or even optimizing the manufacturing process of energy-intensive production of ceramics, for example, and other components. Hand it over to you, Michel.
So hi, everyone. So Michel Hunsicker. I'm part of EDF Pulse Ventures, the corporate venture capital fund of EDF. So EDF is a European utility, so we operate a very large set of assets from nuclear to renewables, hydro, gas power plants. And my background is engineering, and I got as well about more than 20 years in the energy industry. So what brought me here is the fact that at EDF and in our investment activity as well, we are looking for solutions to improve the efficiency of our activities, and basically simulation is a strong part of it. Whether it is used to, for instance, optimize our assets, for instance, in the process, how do I simulate to get some kind of digital twin part, but as well on the material side, because we have a part of our activity that is not always well known, but that consists in manufacturing nuclear reactors through our subsidiary like Framatome, or large steam turbines like Arabelle Solutions. And basically, the topic of gaining time into the simulation and so on is very critical. And for instance, an example that I can give is we are now looking quite deeply into additive manufacturing. And sometimes today, it takes more time to do the simulation of the printing process to ensure that you don't have some kind of residual stress and so on if you want to test a new printing strategy than to actually print the part itself. So definitely this kind of simulation is key for us.
Thank you. Sorry.
Yeah, so I'm the CEO of PassiveLogic, and PassiveLogic makes a platform for generative autonomy, so the ability for you to use our Autonomy Studio software, build your own custom world model in a matter of tens of minutes, maybe a few hours, and then drop that on a general purpose autonomous platform to control infrastructural robotics. So what is infrastructural robotics? It's buildings, it's data centers, it's logistics centers, it's all of the physical world around us. They're the most complex robots we build. They just happen to be bolted to the ground. So when you look at the transportation world, things like a Waymo or a Tesla, it's the same idea, but applied to these complex things like the building that we're in. And the thing that's maybe not obvious to everybody, if you don't see the underlying lives of this infrastructure, things like buildings, a building like this probably has around 5,000 I/O. So that's sensors in, controls out, where a Waymo has maybe 75 to 100, where it's got 50 or 75 sensors in, and it does three things. It steers, brakes, and accelerates. So we have all this complexity in our hard assets that today is under-controlled and under-managed. And if we just look at the potential of this from an energy perspective, because we're at an energy conference, buildings are about 45% of all energy. 40% of that, according to the Department of Energy's in the US's own numbers, is savable just through better control. Right? So you multiply those two things together, that's not like turning gas cars to electric. That's like taking all transportation and evaporating it from the planet. So the potential on the energy side is great, but the fundamental, how do we operate these assets in an efficient and effective way, and how do we democratize the automation space so that we can actually get from the very narrow application of automation today to getting it to 100% of these assets.
Thanks, Troy. You know, it's amazing when you are intimidated by a panel. And when we were doing our pre-call, I live out in San Francisco. I'm a venture capital investor. We have a fund that does growth capital investments. I think that AI is permeating everything that we do. And so what's interesting is how physics AI is going to get into that narrative. Maybe we could start with the idea of why aren't the current models working? Like, what is it that you believe that the generative models are not doing well enough that you think that physics AI is going to be able to solve? Maybe we could start there.
I mean, especially in our space, so computer-aided engineering, right? It's a space that is like where the data is scarce, right? And normal machine learning models requires a lot of data. Unless you have a lot of data, you're not going to be able to train them effectively. So you need to find an alternative to these models that require a lot of data. And the way to do it is by embedding the physical laws directly into the model itself. And this simplifies training and also enhances the results of the output of the model itself.
When you say physical models, you're actually talking about like the laws of physics, thermodynamics, mechanicals.
Yeah.
Is that correct?
Yeah. So conservation laws, differential equations, you can extrapolate parts of it and implement it directly into the solver, right? Especially like what Michel was mentioning for safety critical applications. You need to ensure to the engineers that the results are accurate. Like even 98% of a probabilistic approach is not very good for an engineer in certain cases, right? So you need to make sure to bypass this limitation of probabilistic approaches.
yeah, you can't really do a recall of a wind turbine that's 98% accurate, right?
Yeah.
So, and I know I want to talk about that a little bit when we start talking about how this is practically going to work. But Troy, I'm curious, when you're thinking about how physics-informed AI is going to work going forward, how do you think about it that are traditional ML models going to eventually advance quickly enough? Or take me through a little bit of where are we on the cycle?
Yeah, so at this point, everybody is well immersed in using language models. But we gotta imagine for a moment, so you're about 3 years into the language models being really pervasive on the public market. These are probabilistic word choosers. That's all it is, right? So ChatGPT isn't actually intelligent, it's just really, really good, like, speaker, right? It's a really good vocabulary, semantics. And so when we go to areas that require accuracy guarantees that it must be controlled right, we need new kinds of AI. And transformer models, which underlie these language models, they're known to not, in fact, it's proven that you can't guarantee their outputs. Right? So if we want provable AI, and we want one other thing in our case that's important. So AI is tremendously successful at training on things that would take a huge team of engineers, long periods of time to model. But at the same time, it's breaking the fundamental law of every single thing that we've put into computer science for the last 70 years, which is composability, right? All these models are monolithic, and you can't pull them apart. So you see something like a Waymo, and they've been working on this for, I don't know, 15 years. Now, if you notice the trend upward, all of the last gains have been in the last 3 years. So at 3 years, 4 years ago, those Waymos were about 30% as good as a person. They're now 1,000 times better than a person. Why is this? Because it's reinforcement learning on physics models. So they're pre-trained on physics. So what if we made composable models that understood their ground truth, understood the physics, and now we could make them compose, meaning you could take fragments of models and create wholly new models that nobody's seen before without a training period in a matter of minutes. So this is one of the fundamental things that we're solving, which is if you need to be able to apply it, not just to a niche application, but in any application, these model fragments that you can compose into a new model need to be able to understand their ground truth. What is a good ground truth? Well, physics is a proven ground truth for most of the, especially the physical world, right?
Physics existed before we were here, and it will exist after we're here.
Exactly.
So
It's not a human construct.
it's not a human construct. Well said. Michel, I'm curious, when you're thinking about, let's assume that these models are being used effectively, what are the barriers to adoption? When does industry embrace this and say, we're going to have massive rollouts through our engineering teams? What is it that you're looking for? I think you have a great perspective being on the investment side, but also as a practitioner.
So I guess it relates to what has been said. It's the fact that if we can't move beyond the black box of the current models, then it will be difficult. I can, for instance, illustrate that with what we currently do. For instance, when we use some kind of simulations and so on for the nuclear industry, you have to take months, if not years, to get it certified by the Nuclear Safety Authority. And the point is, currently, for instance, we have, when we discuss about materials and fluid dynamics or material testing and so on, we have, I would say, some even internal models that we have outsourced, and it took, I would say, a lot of time to get the certification. And now to switch to a new model, when people and the engineers are seeing that, they say, oh my God, it will not be possible to convince the nuclear authority because we had to go through all the entire math of the simulations that we have approved. And I guess it will be, if we manage to go and to reach this step, then it will move, and maybe a kind of middle way with an hybrid approach could actually help going there. What we see as well is, to some extent, for some modeling, we see some moves. For instance, we have, and you may want to discuss with them, a company called Metroscope. They are actually simulating, for instance, power plants. So it's not deep neural networks and so on. It's more machine learning with Bayesian approach and so on. but it's now it has been deployed on the entire nuclear fleet of EDF and as well on some other, on almost 100 power plants. And for that, we are reaching on the process, it's okay, but for the very, I'd say, specific CFD or finite elements, for those who know simulations, then I guess there is still some way to go and some work to be done.
You know, a lot of these language models, their data sources are images or websites, et cetera. How are these models learning? Where are they getting their sources of truth?
Well, I think this is actually the critical point of why physics-informed models are crucial for all of these next generation applications. Because think about language models, it seems like such a revolution, but in fact, like I guarantee you, all your kids in the next few years in middle school will be making their own language models because it's easy. There is tens of thousands of human experience in all sorts of languages that we've been going around and labeling things, table, share, you know, in all these languages, right? And what we've done is co-opted now billions of people to put it all up in one big data repository, the internet, and now you can just scrape it and you can make a language model. So it's becoming very, very trivial to make language models. But for all the other applications, where's the data, right? You don't have tens of thousands of years of people scraping, like naming and labeling things and hoist it onto the internet. So you're gonna need another source. And that source either is gonna come slow, or you take the fundamentals and you infuse it into the model itself so that it already knows what are those basic laws of the universe.
And Alex, you talked a little bit about how the underlying models are moving from kind of these deterministic and probabilistic models going forward. You know, how big can this get? Like, is this applicable to all of AI, or is this going to replace every type of simulation that we're going to do? And I'd love to understand a little bit if we're thinking now about 5-10 years out, what is the role of an engineer inside of this type of new world that we're operating in?
Yeah. I mean, replacing is a big word, so I'm not sure I feel comfortable using that, but let's say going into that direction.
It's my exoskeleton.
I would say, so there are some things that I see happening for sure in the next 5 to 10 years, and some things that I hope for them to happen. Definitely, we are gonna, like with these models, we are gonna lower the entry barrier to the hardware space, right? Making it easier for more entrepreneurs to work on hardware problems. And you can see it already from the space economy, right? It's fastly growing. Someone built the first reusable rocket, and now everyone understands how you can reduce the cost to manufacture these parts, and with simulations you can do even optimize this process even further, right? This is the first point. Second point, I see many more employees within these large engineering companies starting to adopt techniques that were very specialized only for simulation engineers. So a designer, a product manager can make their own assessment on how a specific combination of parameters performs in an engineering environment, which would shorten significantly also the interaction across all these teams within large enterprises. The third point is about digital twins, right? So digital twin has been a big topic for quite some time, and the limitation of these twins is that they are a static replica of something that actually changes dynamically. And the reason why they're static is because simulations take a bit of time to converge, and whenever you're updating a new parameter, you need to rerun the simulation and give the output to this twin, which is not really a twin, right? It doesn't deform live as the real object is deforming. So accelerating these simulation tools would also allow to really have real digital twins. The two topics that I hope for, one of them is programmable physics, right? So at some point we're going to get to a situation where an engineer would define an objective function, some constraints, and the model would go and explore the solution space for that specific problem. And yeah, this is the most exciting one for me. Another point is continuously evolving systems, right? So you give the ability to this engineering system, let's say a power plant, to simulate continuously how the model behaves in changing conditions,
in a real life
record it
environment.
from data, and then adjust accordingly. So we're going to move to a point where the limitation would be basically in the ability of the user to define the right problems.
You know, one of the things that at our firm that we're hyper aware of is data security. And Michel, I'd love to maybe ask you to think about, as you know, if I'm a chip designer, I'm going to let somebody behind the firewall to help me understand this new type of chip geometry that I'm building. How worried should we be about data security, and is that a limiter to ultimate scalability of this product?
It's a really good question, and if I take, and again, I'm going to maybe the most demanding, I would say, part of our business, it's nuclear. And when it comes to data security, there is one first thing that we ask whenever we discuss with some, I'd say, solution provider: do you provide on-premise solutions? Otherwise, for many of them, it's a no-go. Because we don't, it's so critical, those data are so critical, and the fact then that you could get some kind of people moving, tampering with the data and so on, it's so critical that if this option is not ready, we just say, unfortunately, we can't move further. So that's one of the key parts. Then there is as well the topic of the data hosting, where is it hosted, and regarding all the, let's say, the evolution of the world currently, the sovereignty part is becoming, I would say, very, very important, if not more important than in the past. So that's definitely two aspects that we as a utility would look when looking at a solution provider. But the on-premise, for many of them, when it comes to critical, is key. Otherwise, there is even no way to get into a nuclear plant at all.
I mean, I think as you point out, these are very high-stake environments that you're working in. It's not one where you can do a correction and say, I'm going to recall this email or change the way that this prompt works. It's critical. Troy, you're working in buildings. Tell me a little bit about how you think about data security and sovereignty, and how do we ensure that these physics-based models will retain it? Is it being on premise? Is it being behind the wall? How do you think about it?
Yeah, we work in real-time systems, and so whether you're automating sort of logistics center or automating building HVAC systems, these are real time. And it's not possible to do that from the cloud, right? You can't, say, drive a Tesla from the cloud, right? You can't drive any of these edge applications. So physical world migrates to the edge. And when you're talking about autonomy, autonomy means autonomy, right? You disconnect the internet and it keeps on going. So that also comes with the security notion of like data's also on-prem. It's learning and its operations is on-prem. And that last piece, learning, is an important piece. When we deal with the world of infrastructure, there's a really unique difference between it and transportation. For the most part, all transportation is the same. I make a Waymo, I stamp out 100,000 Waymos, they're all exactly the same. It doesn't matter if they're driving here in Bilbao or in San Francisco, in Germany. The rules are virtually the same, very, very little difference. But this building and the building across the street and the manufacturing center down the road, they're all different. And so you have to have that generativeness, what is your application, but also means learning must happen on site. So we deal with another kind of security in that we've built these general purpose foundation models that understand the basics of you plug in and it starts operating. It can understand the ground truth of its physics and therefore how to operate the systems. But it can also do another trick, which is important to data security, which is learn on site, learn to your systems, not learn generally, because the general is way more expansive than any one application.
I think we've got about 5 minutes left, and I'm going to maybe wrap up with Two observations that I would have. The first is that it feels like we're in a world of a zero sum. When somebody wins, somebody loses. I'd love to understand, how do you see the next 5 to 10 years? And we'll go down the line. Do you see this as a zero-sum game where people will have labor issues and job issues being changed over time? Are engineers going to be out of work? And I know that we talked a little bit about this, but I'd love to get your sense as to, if we're doing this conference in 5 or 10 years, what are the top 1, 2, or 3 things that we'll be talking about?
I don't want to repeat what I mentioned already before, but I would definitely imagine that, what is a barrier today, for example, for our application is the talent gap, right? So engineering and machine learning are two completely different disciplines at the moment, and if I talk to my peers that are studying mechanical engineering now, they will not know enough about machine learning to apply to real problems. So I do expect the education system to evolve, update a little bit globally, and make sure that we are reducing this gap in terms of education and how engineers can adopt and remove also a bit of skepticism. So this is something that we notice already with enterprises. Everyone knows a little bit about surrogate models, machine learning models applied to engineering problems. So we are already getting there. But I still notice, especially in some academics or other more academic-oriented people, that there is a bit of skepticism. So definitely this will go down.
It always starts like that, right? The academics are skeptical, then the engineers break it, and that cycle keeps going back and forth until it becomes
and it's even funnier than that, because they were the one providing initially the infrastructure to solve these problems, right? The first Fourier neural operator, all these transformer models applied to physics, they come from academia, right? Then they were tweaked, changed completely, and applied to real engineering problems.
AlphaFold was amazing. I thought that. I was like, what just happened there? So that was amazing. So.
Yeah, mostly this.
Michel?
Yes, I would definitely relate to that. I don't expect, I would say, the engineering work and tasks to radically change tomorrow. But maybe the good example to illustrate as well what has been said before is the discussion I had, I would say, 2 weeks ago with one of our colleagues at EDF that is part of the team that actually supports all those open source models to do CFDs and so on. And basically, they are already looking at doing some hybridation and thinking about, okay, I will use for the first 5 iteration, I will use my existing model, but then I will put this AI model in between to do an additional iteration and gain some valuable time, and then come back for the next iteration to the model. And I see some kind of trend to go in this direction to save time and to be more efficient.
Amazing. Troy, you have any?
Yeah, I think I'm actually really optimistic about this next phase. As we're rolling out in volume, we're rolling out at the top side with big enterprise partners, big REITs. On the bottom side, we get to work with blue-collar installers and contractors. And I'll tell you, this is the first time they've felt technology inclusion in their whole career. They felt left behind for 20, 30 years, and finally somebody comes in and treats them like grown-ups and says, AI's for you too, and by the way, we've built AI tools for Boiler Bob and HVAC Harry that you can build your own custom AI models. That's really empowering. And so what we, I've had a chance to talk to like the HVAC union in Canada, and after that talk, the person who ran the union classes was like, that's the most attention that we've had to any topic in the 20 years of doing this. And what I thought was important about it is it wasn't a dumbing down, right? It was translation into their world, But I think that there's so much inclusion that has yet to happen in the tech market, and the AI is the catalyst for a lot of this inclusion.
You know, I'll leave it with this, is that I was talking to my mom before I came here, and I was like, hey, do you know anything about physics AI? And she was like, no, but let me put that into my LLM model and let you know. And I was like, well, next year we're going to be talking more about this. So I hope you had a chance to learn something. I think our panelists have been great. You know, join me in a quick round of applause, and thank you very much for your time. Thanks, guys.